Hello, my student, and welcome. This is Dr. Sirme. For today, or rather for this video, I want to take you through KCSE Chemistry, that is KCSE 2023 Chemistry Paper 2, as it was presented to the student and as it was marked. So stay put to the end. A very nice revision work for you here. This is KCSE 2023 Chemistry Paper 2, and it is revised by Dr. Sirme. Well, this is how, or rather the areas that were examined. If you can look at last year's paper, it had 7 questions. As usual, remember this is a paper 2. A paper that contain long structured questions. Like question 1, you can see the chemistry of period 3 structure and bonding. That is basically form 2 work. You can see question 2, organic chemistry 1 and 2 combined. Yes, form 3, form 4 work. Then there was a rates of reaction or reaction rates, and there was a graph there, question 3. Question 4, some form 1 work, heating curve, and some energy changes. Question 5, electrochemistry, well covered there. That is electrochemistry, yes. Question 6, gas laws, form 3 work. Question 7, some bits of salts and the solvay process. So if you can consider exactly what happens there, this is mainly the breakdown of the 4 classes, or rather the work of the form 1, form 2, form 3, form 4 as it was covered. You can see this paper, it's not for the form 1. So look at that, 4 marks, form 1. Form 2, 23 marks from form 2. Form 3, you can see 21 marks, and form 4, 33 marks. So if you can put together the form 3 and form 4 work, you'll agree with me, student, that this paper requires you to having understood form 3 and form 4 work. It is mainly from the 2 forms. Having done that, I can take you through okay, that note, very important. If you revisit most of my videos, over 50% or rather 50 marks out of 80 of this paper, I have already discussed it here in one way or the other. Moving on, now let's look at the question paper first, because I do prefer taking you through the question paper without the answers, my student, so that now you can have a trial. You can try it yourself before I take you. That was the cover page. That was the cover page. Some few instructions that my student, I may wish you pay attention. Instruction part C. Answer all questions in the spaces provided in the question paper. What exactly do I want to say here, my student? Order in your working will help the examiner marking your paper have it easy and maybe able to see a point that you want to derive home. So it's good to stick to the spaces provided. In case you have misused your space, direct the examiner. Direct the examiner, maybe the working is at the back and the like, so that it will be easier for the examiner to see your work. Part E, all working must be clearly shown where necessary. If it is calculation, do not just press your calculator then transfer the answer. Let it be written down. Let the examiner see your working clearly. Instruction part H, candidates should answer the questions in English. Most of you will say, chemistry, they do not mark language, they don't do grammar, but any word that you write that will bring another meaning in English, actually it will deny you the mark, or rather you will not get the marks. So try as much as possible, my student, to answer the questions in English. Well, that's a breakdown, the grid breaking down the questions, and the marks awarded for each. So there's nothing much to say there. Question 1, my student, you can see question 1 there. Part A, B, and C. what you need to do is to pause the video and maybe attempt the questions. Question 1 continues, that is part D and E. Moving on, that is question 1 continues, part F. Yep, you can see the part F, and I guess that was the very last part of question 1. Moving on to question 2, a question on organic chemistry. So that's question 1, question 2, A and B. Question B continues there, number 2B. Number 2C continues. You can see there's a flow chart. You need to study and answer the questions. Remember, I'm just taking you through the questions so that you can attempt before we discuss the questions together. That is question 2 continues. You can see question 2 is moving on there. That's the end of question 1. Question 3, a question on reaction rates. So question 3, part A and B. Part C of question 3, that takes you to the graph work. Yes, that is question 3C. Question 3C continues. Now questions from the graph. You can see now that is question 4. There's a heating curve there. Form 1 work. Then question 4 continues. That's question 4. Taking you to part B, some bits of energy changes. Yes, questions 4 continues. Question 4, moving on, that is part C. Then go on to question 5. Question 5, electrochemistry. Then question 5 continues. That is question 5, moving on. Some bits of Faraday's law there. Then question 6, gas laws. Yep, question 6, A and B. Question 6, part B continues. You can see my student. That is part C of question C, some bits of calculations. Then move on to question number 7. That is question 7. Good. Question 7 continues. You can see it's the Solvay process, not necessarily a flowchart, but that's a Solvay process. That is the end of the paper. That's the last part of question 7. Good. So what do you need to do, my student? Just stop the video, or rather replay the video. Go through the video, try to attempt the questions, so that when we go through the marking scheme together, it will be very easy for you there. As you go through the question, or rather you attempt the question, I take some bits of hot water. Okay, my student, having gone through the question paper, now we can go through the marking scheme. Now, the marking scheme of KCSE 2023 Chemistry Paper 2, as it was presented to the examiner for marking, and all points well explained here by Dr. Sirme. Question 1, as you can see there, the student was provided with a table containing elements of period 3, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. The atomic numbers were given from number 11 to 18. The atomic radius in nanometer was also given, as you can see. Question A. The student was expected to write a compound, or rather the formula of the compound formed when aluminium and sulfur combine. So as I have highlighted over there, you can see the student was expected first of all to write the electron configuration of the two elements, and that is with an intention of getting the valency. Like you can see, the valency of 3 for aluminium, the valency of 2 for sulfur, because it requires 2 electrons to be stable there. So with that, the formula will be aluminium taking up the 2 from sulfur, that is the valency, the exchange of the valency, and sulfur taking up the 3. So with that, the formula will be as it is given: aluminium with 2 there, sulfur and 3. So the name of this is aluminium sulfide. Some student decided to call it aluminium 3 sulfide. No problem, provided my student you note it is sulfide, not sulfate. I hope you get that and you've gotten it well. That was question 1, number 1. Going on to question 1, part B. The student was to use the very same table and then explain the variation in atomic radii or areas of the elements across the period. So my student over here, there was a free mark just to state. First of all, if you are able to state, look at the trend: 0.186, 0.160. Look at the trend, look at the trend, look at the trend. So my student, even before you explain the stating of the trend, it is a free mark. Because how was the student to score in this question? First of all, just state that the atomic radii will decrease across the period, as you can see the trend. So my student, that was a free mark there. Now come to the explaining why the atomic radii will decrease across the period. And this my student should note, because many students have never captured this. But across the period, there's always an increase in the number of protons, what we can refer to the nuclear charge. The nuclear charge is what pulls the energy levels closer to the nucleus. So the more the number of protons, the stronger the effective nuclear charge, and the smaller the atom will be, because the energy levels will be attracted very close. And basically that is what my student, you are supposed to explain here. That there will be an increase in the nuclear charge or the number of protons that leads to a stronger nuclear pull, or that leads to a stronger effective nuclear charge. That is question 1, part B there. My student, get it well, stop the video, read it through and understand. That is question C. My student, the question was, using the very same table, you select the element with the highest ionization energy. Ionization energy, the minimum amount of energy required to remove an electron from the outermost energy level of a gaseous atom. Okay, the smaller the atom, the stronger or the more the energy required to remove an electron from the outermost energy level. Just that. So in this case, the atom, or rather the element with the highest ionization energy, will be, my student, you can guess before I reveal it. Yes, argon. If you look at the table, it has the smallest. It has the smallest atomic radii, or rather atomic radius. If it has the smallest, that means it has the highest. Actually, with even the noble gases, it is not even easy. Under normal conditions, the noble gases do not lose electrons. It's not very easy. And the reason to that, it has the smallest atomic radius. That's what you're given in the table. Otherwise, if you say it has the strongest nuclear attraction, it's okay. If you say it has a stable electron configuration, maybe having written it. If you say it's a noble gas, you score. But the very first point there is the main, because you are extracting your answer from the table. Good. We move on, my student. Question D, or rather number 1D. You write the electron arrangement of phosphorus in this compound, phosphorus chloride there. Okay. 2 ways of approaching this, my student. Remember the answer was either 288 or 282. And I'm going to explain as to why the 2 answers and how did the student arrive to the 2. Good. Look at this. This is the same compound, phosphorus chloride. I've drawn the dots and cross diagram, the Lewis diagram for this one, and you can see, if you consider phosphorus having shared 3 pairs of electrons with the chlorine, you can see this one, you can see this, and you can see even this one here. Those are 6 already, and a lone pair of electrons there. So in total, these are 8. So it is 288. Remember, there is the first and the second energy level that I've ignored inside there. So that is case number 1. Case number 2, or rather the student could have calculated the oxidation number of phosphorus in this compound. So you can see the oxidation number of phosphorus is X. The one for chlorine is -1 times 3. There are 3 of them, equals to 0. Then you work out, you get 3. What does that mean? I'm working with phosphorus 3 plus, or rather 3 positive. That means it is phosphorus number 15, subtract 3, you get 12. So 12 electrons is the same as 282. Well, my student, that's how the student was supposed to reason for that question. And I know either way, the student could have reasoned out and get the answer like that. This is question 1 part E. Select the elements which form an ion with the smallest ionic radii or radius. Well, we know metals will form ions and their respective ions will be smaller. The non-metals will be larger. So for that case, we can argue with metals, because ordinarily it is the metals that will form ions that are smaller. We think about group 1, group 2, group 3. Leave alone silicon, because it's a betaloid. So let's think about the first 3. If you reason out like that, aluminium, that is element number 13, will be the one forming the smallest ions. So the answer was aluminium. The reason, it loses the highest number of electrons, or 3 of them, hence has the strongest nuclear pull for the remaining electrons. As simple as that. And this is where my student, I said, be careful with the language, the spelling there. Because look at that answer. Almost the same as the first one. But the student could not score because of this. Yes, loses. This is different from the actual one that you should write there. So my student, beware and do not miss the spelling, or rather bring another word that is different. So note that. So for this question, that was the answer. Come to part F, my student there. Yes, part F. The student was given another table with elements sodium, magnesium, chlorine, and argon. You're also given the melting points, as you can see. So the student was to explain in terms of structure and bonding the difference between the melting point of sodium and magnesium. For this case, stating did not score any mark. So you can see over there, and you can see the other one there. We have the sodium 98, magnesium 650. Explain the difference. First of all, anytime you're talking about melting, boiling point, those are physical properties. And the way to answer the question, my student, you must talk about structure and bonding. Structure and bonding. So how was the student to argue out this? 1, magnesium has more delocalized electrons than sodium that has less, or rather you can say magnesium has 2 delocalized electrons per atom, sodium has 1 delocalized electron. Remember, it is the delocalized electrons that are contributing to the metallic bonding. So they then say, hence, magnesium has stronger metallic bonds than sodium. Do not forget to say than, because you are comparing. It's comparative here, my students. So you have to bring in the other elements as such. So for this question, maybe most of the students scored 1 mark because just stated magnesium has stronger metallic bond than sodium. Tell us why. Why stronger? And this one I have to emphasize, my student, because you have to know. You have to read the mind of the examiner. Read the mind of the examiner. What exactly is the examiner expecting you to say? Moving on to question 1, part F. I think it's similar to the question above there, my student. The students who are expected to explain in terms of structure and bonding between the difference between the melting point of chlorine and argon. So as you can see, you are given the melting point of chlorine is there, the argon is also there. So the one for chlorine, as you can see, it's higher than that of argon. So as we have said with the other one up there, my student, it's a matter of arguing with the structure and bonding. So that is the answer, my student. Chlorine has diatomic molecules, while argon has monoatomic molecules. So that is the catch. That is what was calling. Chlorine being diatomic, argon is monoatomic. And that means chlorine has more van der Waals forces, not stronger. It has more van der Waals forces than argon, that is monoatomic. So what exactly do we say? If you think about chlorine molecule, it has 2 nuclear centers. So, and remember, the origin of the van der Waals forces are the nuclear centers and the electron clouds of the other molecule. So there will be more van der Waals forces in chlorine than in argon, that has only 1 nuclear center. So remember, chlorine diatomic, argon monoatomic. Well, that was question 1, and that was the end of it. A question from Form 2 syllabus. Let's go to question number 2, my student. That's question 2, part A. Calcium carbide reacting with water. Then the student was supposed to complete the equation, just like I've done there. Calcium carbide reacting with 2 moles of water, you get 1 mole of calcium hydroxide and ethine. Remember, this is formation of ethine, the first member of the alkyne series, or rather homologous series. This must be balanced. If you like the ethine, you can write in any of the 2 ways. Okay, this is question 2b that had an error. Yes, my student, I hope you can notice something here, that the carbon over here should have a maximum of 4. 1, 2, 3, 4, 5, 6. So this was an error. And that means you will agree with me, the papers, the KCSE papers are set by human, so they're subject to error. Now, for this one, being a revision paper, I've corrected for you something here. The correct formula of pent1-ine ought to have been this one. This should be a triple bond. It is a pentyne, then the rest of the carbon as it is. So if I correct this for purpose of your revision, then there is a compound B, pent1-ine reacted with a bromine, you get a B, compound B, then another, maybe 1 mole of bromine, you get C. So in other words, what are we doing? We are trying to break the triple bond one at a time. So if I add the first mole of bromine, I'll open the first bond. Maybe I get an alkyl. Then I do the second one and I get an alkane with A. So we can see now compound B and C. What exactly are they? So compound B, most likely it is a 1,2-dibromopent-1-ene. It's an alkene. The double bond opening, 1 bond opening, and then the carbon atoms are attached there. So if I continue with another 1 mole for this towards this, I'll get 1,1,2,2 tetrabromopentane. Maybe this is for the purpose of revision, but when it comes to KCSE, the way the question was treated was a bit different. It's a matter of cancelling the questions maybe and redistribute the marks. But in case there's a problem, a setting problem in KCSE or any national paper, my student, I may encourage you to attempt the question anyway, so that when they're marking, whichever the case, you'll not be disadvantaged in any way. Sometimes they will overlook the error and the student will be disadvantaged. Remember, nobody will be there to correct your work, or rather to do a correction. Yes. Well, having said that, let's look at part C. This one, the student ought to have revised. Not revised, studied. You study the flowchart. Before you even go to the question, look at this. The chart starts somewhere with ethene. Ethene undergoes a step 1 to a polythene. So automatically that must be polymerization, step 1. Step 2, ethene becoming ethane. So for you to break the double bond, there must be hydrogen. So like in this case, so this is hydrogenation. Okay, going to this one, step 3, ethene becoming ethanol. This must be hydrolysis. You've added the OH somewhere. Okay, step 4, ethanol to ethanoic acid. That must be oxidation. Then from there you have ethanol and ethanoic acid combining. This step 5, this must be esterification. The ethanol and ethanoic acid esterification. If you are doing this, my student, as you write down, it becomes very easy, because when you're answering the question, you can now see the working, or rather the answers there. Ethanoic acid becoming sodium ethanoate. Yes, you must have reacted with a base. This is an acid, maybe a base, sodium hydroxide, for instance. You get that. Then sodium ethanoate, you intend to get methane out of it. This must be the reaction towards preparation of alkanes. So this must be soda lime. Okay, my student, and therefore we can move on to the questions. That is question 2, part C. Now, Roman 1. Give the reagents and conditions necessary for step 2. Step 2, this one, we said it's hydrogenation. For hydrogenation, you need a catalyst, and of course the reagent is hydrogen. So there it is, the reagent, hydrogen gas. Remember, you can as well write in the formula there. The condition, you need a catalyst, specifically nickel catalyst. The student is allowed to give a specific temperature between 150 to 250, not a range. I've written a range here, but my student, you should know. Be specific, state a given temperature there. You can also use a palladium or platinum catalyst, will also work. As I've said to my student, once you study the flowchart, then answering the question becomes very easy. Look at that one, the reagents and condition necessary for step 7. Let's see step 7. Here it is, sodium ethanoate becoming methane. So this one you need soda lime, or rather you can say it's a mixture of sodium hydroxide and calcium oxide. The condition necessary there is heating, not warming. My student, you should know it is heating. Good. We are done with C Roman 1, part 1 and 2. We move on to question 2C, Roman 2. You write an equation. The student was to write an equation for the reaction taking place in step 1. Step 1. For this one, a majority of students could not write the polymerization equation there. And then step 3, ethene becoming ethanol. Let's see how the student was to respond to this question. Okay, in step 1, here it is. You have the monomer here. In this case, the monomer was ethene. And of course, the polymers, you can see the way we write it with the capital bracket there and an N. And the N here must be indicated to balance. Not a 2, not a 3, not a 10. Because when you're talking of polymers, we talk of hundreds of monomers. Actually, thousands. Well, my student, that is how this question was to be written. Maybe most of the students missed because of the balancing. The writing of N there was not there. And of course, the rest of the logistics there. Okay, part 2 of the C, question 2C, Roman 2. You can see we have ethene gas reacting with water molecules in presence of concentrated sulfuric acid to get ethanol. Remember, this water is a reagent. This concentrated sulfuric acid is a catalyst for this case. So the equation was to be written like I have written. Alternatively, the student could have decided to use concentrated phosphoric acid. The other condition must be specified 300 degrees Celsius, 6, I think it should be 6 atmosphere of pressure there. Otherwise, again, this was a question that was very tricky for the most student to write it down. The step by step, a student can decide to do a step by step approach, and still it is acceptable for this. It has two, remember it has the 2 steps as it is in I think it is in book 3 or thereabout. In case you use the second one, the water must be in gaseous state there. So some of the questions there, they were tricky, but not tough as such for students to do. Next is part C, Roman 3. The student was to state the type of reaction in step 4 and step 2. Let's go back to the flowchart. Ethanol becoming ethanoic acid. Yes, I think when we are studying already we knew or we stated what it is. Then step 2, you have ethene becoming ethane. So step that is step 4. This is oxidation. The other one is step 2. This is a hydrogenation, or rather, my student you can just say it is an addition hydrogenation. Don't just say addition. Addition will not score because there are several types of addition reaction. So if you say addition of hydrogen, it is well and good. Let's move on. The student was expected to draw the structure, and anytime the student you're told to draw, you're supposed to do the open structure of the compound. That is now the drawing, not the formula, not the molecular formula as simple as you can look at it. It is the open structural formula. With that, the compound D, this is an ester, and of course you give the name. As you can see, my student, there it is. All bonds well illustrated. All bonds well illustrated without a missing hydrogen or oxygen or carbon. That is it. The name for this, it is you start by naming this end that came from alkano. So it's a 1, 2, this is an ethyl. Then on the other side, you have the 2 carbons and the alkanoid part. So it is ethyl ethanoid as one word. That is the end of question 2, my students. Yeah, we can move on to question number 3. Question number 3. Okay, explain how increase in temperature affect the rate of a chemical reaction. Anytime this question is mentioned, talk about collision theory. You cannot explain how such a factor affect the rate of a chemical reaction without considering the collision theory. But the first mark is free, my student. What you need to do, state how increase in temperature affect the rate of a chemical reaction. From there, the rest you can maybe try to score. So an increase in temperature increases the rate of a chemical reaction, 1 mark. Okay, that is due to the increase in kinetic energy of the reacting particles. Remember, increase in temperature increases the kinetic energy of the reacting particles, and that means the particles will be moving faster, and that increases the number of fruitful or successive or effective collisions because they can collide more, and the more they collide, the higher the chances of them colliding with sufficient energy in the right geometry to produce the products. Question 3b. Consider the reaction you're given. You have nitrogen 2 oxide reacting with hydrogen to give you nitrogen 1 oxide and water in steam or in gaseous state. Explain how increase in pressure affect the rate of a chemical reaction. One thing, my student, you should know is that this equation has nothing to do with an equilibrium. This equation has nothing to do with the reversibility of the equation or the reaction, because they have talked about the rate of this reaction. So do not consider, I don't know, 2 volumes of NO, 1 volume in total, you have 3, on this side you have 2. No. Consider the reaction itself without the reversibility. So increase in pressure increases the rate of the forward reaction. Or rather, the rate of the forward reaction is increased, 1 mark, without too much of any of reversibility. Then you state at high pressure, particles are brought together. When the pressure is high, the particles are pushed very close. And when they are very close, they can collide many times. And because of the many times they are colliding, therefore the effective collisions are increased. Okay, my student? High pressure, the particles are pulled together or they are brought together, hence they collide even more times. That is how the student were to answer that question, as simple as that. Question 3C. You're given at high temperature, these 2 gases will react as given. Yes. Then the reaction was monitored. Yes. And the changes in concentration of NO, nitrogen 2 oxide, with the time was recorded as follows. Time is given there from 0 to 300 seconds. The concentration in moles per liter was also recorded as given. So the student was to use the data and plot a graph, or rather draw a graph of concentration of NO against time. The questions on graphs, my student, will often be there. If not in paper 2, they'll be in paper 3. So it's good, my student, you learn how to draw a graph. What do you need to know, my student? How to choose a scale. Okay, of course, labeling of this axis, plotting and drawing the curve. As simple as that. Now, this is the exact space that the student was given. And if you consider, like along the x-axis, 1, 2, 3, 4, 5, 6, 7. So along the x-axis, the student had 14 centimeters. And I'm doing the physical counting because my student, when the paper is being marked, physical counting will be done for us to ascertain if the student has used the right scale. So if that is the case, considering I had from 0 to 300, now consider the scale I've used. For every 1 centimeter, 25 seconds. So with that, if I consider from 0 to 300, I've used more than half by far. So you can see the choice of scale for my x-axis is okay. If you consider the y-axis, I'm starting from 0 to 32. And I come over here, I do a physical count. 1, 2, 3, 4, 5, 6, and 7. Again, that is 14 centimeters. If you consider how I've chosen the scale here, from 0 to 5 to 1 centimeter, it is 2.5. And that means from 0 to where that 2 will be, I'll have used more than half of it. Actually, by far. Practice, my student, on how to choose a scale, because the choosing of scale will give you a free mark, a whole 1 mark. You can see a scale gives you 1. Now, once you have the scale well written there, then you are able now to do the plotting. You are able to do the plotting very carefully all the way to the end. And having done that, plotting, you score 1. Then for this case, the curve was supposed to be a smooth one, freehand, as you can see there, and you score the mark for the curve. Label the axis very well. Remember, my student, to indicate the 0 point there, the origin. Maybe another very common mistake is where the student maybe failed to make their scale uniform. If you decide to skip 1 centimeter for 25, the other one should still be 25. Another 25, 25, not 25, then 50 and the like. So that is how the student was to do the graph for question 3, part C. Now the student was to use the graph and find the rate of reaction between the 25th second and 75. Then remember this question was there even the other year. And anytime a concept is repeated, it shows that the student are not scoring it well. So this one was there. Then at 75, this is the rate of reaction between 2 points. This is the rate of reaction at a point. And of course, you give a reason as to why there is a decrease in the rate of reaction with the time. So we can look at how the student was to do this. Okay, between the 25th and 75th, you can join with a straight line, then work out the gradient of that line. Try to select, or rather read the coordinates here at 75, read the coordinates at 25, then work out the gradient. And basically that is it for this case between the 25th and that. At 25th, it is 9.5 concentration, 75th, and 19 point that. Then you can do the subtraction. Remember there is a 10 to the power negative 3 there. 75, that is change in y over change in x. Remember the 10 to the power negative 3 there. As you work out that, you get. So, but my student, don't just look at my values and say they were the answers. No. The marking always use the student's graph. Okay? The student's graph that is well drawn. Okay, at 75th. At 75th. So, come over here. That is at 175th. Come over here at 175. Yes, select the point, draw a tangent. Without the tangent, no mark. So, first of all, draw the tangent. The examiner marking the paper must see the tangent. And once you have the tangent touching just a point on that curve at 175 seconds, then from there we can proceed. After drawing the tangent, get any two coordinates along the tangents. Yes, any two coordinates, find the gradient, work out the gradient of that line. As you can see there, according to mine, I had 32 and 250 there seconds, 22.5 and 75. Then you work out the gradient as I've shown you there. This question here, remember the question 3C Roman 2 part 1. Again, it uses the student's graph. The way the student has drawn the graph, the values she has decided to, or he has decided to take, that's what the examiner will use. Question 3 part C, Roman 3. Why? If I can go back and ask you the question, here it is. Give a reason as to why the rate of reaction decreases with the time, all the way from the graph. If you look at this, the rate of reaction as you start is high than when you're coming, or it's coming to an end there. Basically, that's a question that my student should know. That with the time, the concentration of the reactant, for this case, it was nitrogen 4 oxide and CO, carbon 2 oxide, reduces with the time. All it is used up. That is a case, my student. You know, you're asking, why is food decreasing from the plate? It's because you are using it. It's because you are eating it. Okay? So with the time, the reactants get used up. So they will not react as fast as at the start of the reaction. As simple as that, my student. Good. We're moving on well. We're done with question number 3. Now we do first part. That is part A. There was a heating curve. And there's a word here, my student, you must get. And I want to highlight this because this costed the student the marks. There it is. You can see that word. Figure 3 shows the temperature of lead. Lead changes, how the temperature of lead changes as it is heated. Hey, this one. Then Roman 1. Label on the diagram the states present in region C and D, between C and D. These are liquid. Remember, starting from AB, these are solid, then it melts. After melting, this will be a liquid up to D, then it boils, it becomes a gas. So between C and D, it is a liquid or in molten state. Between EF, that is a gas. Many students missed that somehow. Maybe the word state was an issue, but I don't know why. The state of matter, liquid, gases, solids. My student, you ought not to have failed that. Okay, there they are. Whether the student indicated on the diagram or on the spaces given, it was okay. For gases, you can say gases, gaseous state, vapor. Liquid, you can say liquid, molten, well and good. That's fine. Look at that one. Explain why the temperature remained constant between B, C. Remember, this is Form 1 work, my student. But because of this word that I have said just some few minutes ago or seconds ago, the student missed it. You are used to saying between B and C, remember this is the melting point, that the substance, we know it's melting. You are saying the heat supplied is used to break the intermolecular forces of attraction between the particles. All that was costing the student the marks. Remember, we are hitting a metal, so not mention of intermolecular or any kind of intermolecular forces of attraction. So how was the student supposed to respond to this? The heat or the energy supplied is absorbed to convert the solid lead into liquid. Rather, to break the force of attraction, not intermolecular forces. Forces of attraction between the solid lead, hence it changes its state to liquid. Between the other parts, between D and E, what exactly is happening? The heat or the energy supplied is absorbed to convert liquid lead or lead, the way you pronounce that, to gaseous state, or rather break the forces of attraction that hold the liquid particles together of lead, and they are converted to to gases. Hey, my student, this question was Form 1 work, but very tricky. Very few students got it right. We go to part B. This is question 4, part B. And for this diagram, the student was given potassium bromide, solid potassium bromide, and it is converted to potassium ions in aqueous state and bromide ion in aqueous state. On the other side, you have the same being converted to potassium ions in gaseous state and bromide ion in gaseous state. Then over here, the gaseous ions are hydrated. It is as simple as we dissolve a solid in water. This is a solid. It becomes a solution. So this is a heat of solution. Heat of solution directly. If I have this, remember, if I go from the gaseous ions to the solid, this is the lattice energy, the formation of a lattice. But now we're doing the opposite. So this is lattice energy, only that you're talking about the negative of it. Gaseous ions becoming aqueous, that is being hydrated. So we have the heat of solution, lattice energy, and hydration. Actually, the question was, you name the 3 types of enthalpies. So the first one, heat of solution. Here it is. This is heat of solution. This one, heat of solution. I go to this one. The second one, this is lattice energy. Lattice energy, formation of a lattice, the negative of it there. Then you have the hydration energy, that one. The gaseous ions becoming aqueous ions, that is hydration. Good. That is B. Part B, Roman 2. An expression that will show the connection between the 3 delta H. The delta H3 delta H1 and delta H2. Remember, you are expressing delta H3 in terms of the other. So where is it? Here it is. So this is like vector method, my students. If I want to come from the gaseous ion to the aqueous ion here, I can decide to go this way. Okay, so it will be the negative. Remember, this is now positive coming from the solid here to the gaseous ion. So this is negative, positive. So I'm going back. So negative of this, yeah, negative of delta H2. Then this is positive. So in short, how will that look like? There it is. It is delta H1 minus delta H2. If you state delta H2 plus delta H1, you're still right. And that is it. Good. We move on. Okay, using the thermochemical data given in table 4, calculate the heat of reaction given there. Hess's law. Hess's law looks a bit complicated, but it's not. It's not. Look at this equation as it is. Try to extract it from these equations that you're given, the thermo equations that you're given. But let me just take you through this. I know I do not have many people on my side here, but let me just take you through. Let's look at this equation. We have the BF3 on the reactant side. Let's look at it here. Here it is. It is on the product side. So let's reverse it so that it can appear on the reactant side. So once I reverse this and the energy becomes positive, yes, already I have a half a mark. So what have I done, my student? I've analyzed the equation here. The boron trifluoride, or rather BF3, it's on the reactant side. I consider the three equations I'm given. It is here, but on the product side. So I reverse this to make it on the reactant side. And that's what I do. I consider B in gaseous state. Where is B in gaseous state? It's a product. Over here, it's a product. So I let this equation remain. The thermal equation remain as it is. And look at this. We have F in gaseous state. Look at this. F, remember this is not F molecule, F atom. That is a fluorine atom. It's in gaseous state. Here you have F molecules, but the F atoms in gaseous state are on this side. So you let them remain. The molecules remains on this side. The F remains on this side. Once you do that, try to balance that equation as it is given there. Balance together with other equations. Eliminate in a way that you will get the original equation you had here. I know those are things that are not very much understandable. But once you do that, add this. Add the energies and you get the answer. Alternatively, you can decide to draw the energy level diagram. That's called the energy cycle diagram. The original equation you had, there it is. Then consider like which one? Let me see this. You have the second equation here. B reacting with 1.5 moles of fluorine molecules to get this. So I've just used these two to get this. Which equation is that? This one. It is that equation. Then what have I considered? I have an equation converting B in solid to B gas. Here it is. So again, there it is, becoming that. Okay, then I have the final equation here. The fluorine molecules being converted to fluorine atoms. Here they are, fluorine molecules going to fluorine gas. And there it is. With that, I have an energy cycle diagram. Then I intend to move from the boron trifluoride here to this other product. So I'll go against this. If I go against that, it will be negative over negative. So it will be positive. Just like we reversed here. So here it is. So the negative of negative. Then plus. This is as per the arrow you add, as per this arrow you add. And once you add, you get the very same energy there. Positive 1938 kilojoules per mole. I know those are jargons to many students, but love chemistry, love energy changes even when it comes to Hess's law, because the chemistry we are talking about in high school is just but a shadow. I'm not scaring you because eventually you'll find yourself in campus. But beware, the chemistry we're talking about is not that tough. It's not very tough. Question number 5. There it is. You're given a table. These are questions on electrochemistry. You're given a table. Some half cells given numbered 1 all the way to 8. The electrode potential given, the half cell equation, and the E values given. So the student was supposed to select 2 electrodes that gives the least, the lowest EMF. So my student, though I have not indicated this down, but my student, you're expected to take all these numbers given, the E values, arrange them either in an ascending or a descending order, and then start comparing any 2 adjacent values, the one that gives you the lowest value, or rather the lowest difference. And that's all you need to do. Like for this case, though I did not do it, but if my student, you can write down these values. Finally, you'll end up with this, that between tin and lead, or rather the half cell number 3, yes, half cell number 3 and half cell number 6, they will give you the least EMF, the least difference there. So that is how to do it. If they are talking about the highest E value or the EMF, the highest, you consider the most negative and the most positive. Yes, the extremes. If you have your number line, the most positive and the most negative are the farthest. Okay? But for this case, you don't go for the, the least positive, the least negative. That thing cannot work. So be wise and do that very well, my student. Okay, we move on to question number, that is still number 5. Yes, number 5A, Roman 2. Arrange these 3 metals. You given silver, you given iron and tin in order of their reactivity with dilute acid. These are metals. So if I can consider them, I have silver, yes, positive 0.80 there. I have iron, or rather you call it iron, and I have that is tin. We say PO, my student, PO. PO, I mean the most positive is the strongest oxidizing agent. The most positive is the strongest oxidizing agent. And what do oxidizing agents do? They gain electrons. If they gain electrons, these are metals, they will lose electrons. So the opposite is what we are interested with, that the most negative is the strongest reducing agent. So let's consider which is the biggest negative we have here. This is iron, okay, followed by tin, then silver. So if you are considering the answer, it is iron that will be the most reactive, followed by tin, then silver. What have I just said? The most positive, PO, is the strongest oxidizing agent, and the opposite also apply, that the most negative is the strongest reducing agent, the element that can easily lose electron. So out of the 3, as you can consider, this is the most negative. So iron will be the strongest reducing agent, followed by tin, followed by silver. The reason for that, the order there it is, iron has the most negative E value, hence it's the strongest reducing agent, and hence the most reactive. If you like to argue with silver, well and good. It is the most positive, hence it is the strongest oxidizing agent, and the like. That's why it is the least reactive there. I move on to question 5A, Roman 3. An electrochemical cell is made up of the 4th one and the 7th. Calculate the EMF. Calculate the EMF of that. Then you write the equation for that. I've selected that. You can see this is copper 2 ions becoming copper metal. 7, it is copper 1 ion becoming copper metal. So how do we go about that? Either you argue with the formula, my student, that the E cell is always given by red ox, reduction minus oxidation, reduction minus oxidation. Let me take you back. You're saying red ox. What does that mean? The cell that is more positive, like this one, it contains the oxidizing agent. So if this is the cell containing the oxidizing agent, what does that mean? It will be reduced. The cell that contains the oxidizing agent will be reduced. What is reduction? It is a gaining of electrons. Okay, so this one, the reduction cell minus the oxidation, and therefore it will be 0.52 minus 0. Therefore, my student, just applying that formula there, if you're good at mastering the formula, the E cell will be E reduced minus E oxidized. Having done that, we can look at it. Of course, if you subtract, you get that. If you consider this, we've said this, the most positive, it's the cell that has the oxidizing agent. And what will happen to an oxidizing agent? It will be reduced. And if it will be reduced, it is a gaining of electron. You let that half cell remain as it is. Then, of course, reverse the other. And if you reverse, the E value also changes. Once you do that, you can add the half cells and, of course, end up with this net equation. Add up the E values and you end up with this. So, my student, practice until you perfect how to go about this calculation of EMF. Question 5, my student was supposed to come up with the equation. Let me take you back. It's the equation for the half cell between the cell number 4 and the cell number 7. So it's a matter of combining the two half cells, balance the electrons very well, come up with the net equation, and there it is. That will be the equations towards that, the overall there. Remember to cancel the spectator ions. Remember to do away with them. Otherwise, they will add no value. Like if I have copper, one copper is here, the one should go. One should go, you remain with the one, like that. Good. We move on to this question. Draw a diagram of electrochemical cell that can be used to measure standard. Look at this word, standard electrode potential. So that means some issues to do with the standard electrode, or rather what you call the standard hydrogen half cell must be indicated somewhere, and the conditions well indicated. We are combining the half cell 14 and the one for hydrogen, and you can see there the half cell 14 and even the E value given. Good. This one, it's going with quite a number of marks, 3 marks. Where exactly do the examiner concentrate? Like, for example, the concentration of electrolyte, 1 molar. Even on the other side, 1 molar hydrogen ions. Okay, so you can see that is the first half scores. The electrode over here, the tin electrode, dipped into the solution of 1 molar tin ions. And then you have on the other side, hydrogen gas. Being a gas, my student, you need to be very careful. Yes, the gas should come in under the specific conditions, like the temperature 25 degrees Celsius, 1 atmosphere condition. Then, of course, the gas will not just dissolve in water or in solution. You'll have to get a material that can adsorb the gas. Like in this case, we use the platinum plate, or rather the platinized platinum plates. Over here, I must see the salt bridge, whether you indicate what is inside the salt bridge or not, but I should see indication of a salt bridge connecting the two solutions. Over here, I should see a voltmeter. If I see a dry cell, in case the student makes a mistake and draws a dry cell, the whole of that electrochemical cell is wrong. So no dry cell, just a voltmeter, whether you indicate the voltage here or not, but provided I see a voltmeter there. And on this side, my student, on this right hand side, I must see a hydrogen half cell drawn there. That is a standard hydrogen half cell. If not, the working is wrong. So just master that, my student, because just the other day again, there was a question on drawing of the electrochemical cell. Part B, the student was supposed to fill in the product for the electrolysis of dilute aqueous sodium chloride, concentrated aqueous sodium chloride. The product at the anode and at the cathode. Okay. I don't know whether the student you have a problem with this, but the products for at the electrodes depends on the concentration. If you're talking about highly concentrated sodium chloride, the product will be different. So there they are. At the anode, the OH. When you're talking with of dilute sodium chloride, OH ions will be discharged, and then oxygen gas will be liberated. At the anode, the hydrogen ions are in higher concentration. As you can see, the hydrogen ions will be discharged and you'll get hydrogen gas. If we are talking about concentrated sodium chloride, at the anode, it is the chlorine gas that will be coming out. The chlorides are in higher concentration than the OH there. At the anode, sodium will not be discharged. It will not. But hydrogen gas will be discharged, as you can see there. You can revise that, my student. Remember, the half cell equation was okay, but the mention of what will be produced, the product was maybe of interest more. We move on. You're having a question on calculations. You have aqueous chromium sulfate is electrolyzed using inert electrodes. That is the half cell equation. Calculate the time in second required to deposit this number of this amount of chromium, and the current is given there. This is a Faraday application of Faraday's law there. So my student, you can decide to work out the number of moles of chromium. Mass divided by relative atomic mass, you get that. That's where you score half. Then quantity of electricity to deposit 1 mole. Remember, you're given the equation, you're talking about 3 Faraday. So that is 3 times the Faraday's constant. You get the number of coulombs that you need for 1 mole. Then you go ahead, work out this. You say, in case this number of moles gives you, the coulombs gives you 1 mole. What about the, how much of the quantity of electricity will be needed for this? So if you work out, you get the quantity of electricity you need for 0.05 moles of chromium is this. Then use the formula, quantity of electricity equals to current times time. Manipulate that formula to get T, because you know the current, it was given, and of course quantity of electricity you have worked out. Okay, so that gives you the time in seconds there. That is one way of doing it. The second way, there is maybe a number of students who can be able to combine the formulae. The mass deposited will be quantity of electricity, that is IT, times the relative atomic mass multiplied by the number of moles times the Faraday's there. That is moles of electrons. As the student can do that combined, well and good. The working is seen, the questions, the marking point well done, and the answer is correct. The student is able to score the 3 marks, the 2 marks. Question 6, my students. Form 3 work. State Charles' law. My friend, this is Charles' law, not any other person's law. So if you state this law other than the way Charles stated it, then you are stating your own law. Then you use the data given to show that they are in line or inconsistent with Charles or Charles's law. Okay, Charles Law states that for a fixed volume or rather for the volume of a fixed mass of a gas is directly, this is a key word, directly proportional to its absolute temperature is key at constant pressure. Just the way it is. I've said no other law. It is Charles's law. If you state with the abbreviation there, V is directly proportional to T at constant temperature or pressure, it's okay. Or rather, introducing a constant. Let's look at part 2, or Roman 2 here. If you consider this, the pressure is constant. Remember the formula. The formula is the V1 P1 over T1, the combined. But the pressure is constant, you don't consider it. All the student was to do, take the volume, like in this case, take the first volume, divide by temperature. Just its pressure, get the value. Take the second volume, divide by its temperature. And of course, you get the volume, even equating the two, just stating that this part here, yep, and these parts are equal. The student scores the 2 marks. Remember this question, it's either 2 marks or 0 marks. Because it's either you have shown the data is inconsistent with Charles' law or not. So just take the volume, divide by temperature. Show the answer. The volume, divided by temperature. Then show that they are equal. And that is all you need for the 2 marks. State Graham's law. Again, it is Graham's law of diffusion of gases. With that, there it is. The rate of diffusion of a gas is inversely proportional to the square root of its density. Square root of its density. Remember, the temperature and pressure have or has the two conditions must be held constant at the same temperature and pressure. Whether you illustrate with this formula, it's well and good. But my student, either you master the law itself or you do not have it. So learn to master these laws. And chemistry is full of very many laws. Science is all about laws. Yeah. You're given that 1 mole of gas occupies 24 dm cubed at this temperature. Calculate the density of oxygen. Yes, density of oxygen. Remember, density is mass over volume. Then the density of hydrogen gas. There they are. You can work out the relative molecular mass of oxygen, that too. Over here, many students maybe missed to calculate the molecular mass. Density of oxygen, therefore, to be 32 divided by volume. Mass divided by volume. And you get, remember this one. Look at this, my student. It is in grams per liter. You're not supposed to do using any other. So it is the mass per mole, then divide by dm cube. Remember, 1 dm cube is 1 liter. Again, with hydrogen, convert, work out the molecular mass. 1 times 2, get 2. Then go ahead and work out. You work out the density. 2 divided by 24, and you get the answer there. Determine the rate of diffusion of hydrogen, or how the rate of diffusion of hydrogen compares with that of oxygen. That of oxygen gas. It is hydrogen versus oxygen. So how do we go about that? The formula. The rate of hydrogen divided by the rate of oxygen equals the density of oxygen over density of hydrogen. This is inversely proportional. You can see it's inversely. With that, already we had the densities. You can work out, you get 4. Then that's not enough for 2 marks. Just state that the rate of diffusion of hydrogen is 4 times the rate of diffusion of oxygen. Then you can decide to put in words. Hydrogen diffuses 4 times faster than oxygen. Remember, the opposite will not be acceptable, because we're talking about the comparison between the rate of diffusion of hydrogen compared to oxygen. Okay, in case the student would like to use the relative molecular mass, it's well and good. You can see, because already we had the molecular mass of oxygen and the molecular mass of hydrogen. Just like I've done, remember the density and the molecular mass are directly proportional. So with that, just the formula as it was, the same. You substitute the values, get 4. The rate of diffusion of hydrogen is 4 times the rate of oxygen. As we had said over here, it is the same over here. We move on. That is a question on calculations. Yes. Ammonia gas can be prepared in the laboratory by warming a mixture of ammonium chloride and calcium hydroxide. This is a question, we usually use it somewhere. That is Solvay process, manufacture of ammonia. The gas was dried and then collected. If the volume of ammonia collected was this is the volume that was collected at this temperature, 1 atmosphere. Then calculate the volume of ammonia gas that will be collected at this temperature and 1 atmosphere. So this is a question that requires you to apply the combined gas law. For the first time, the student could score a mark by quoting the formula. Yes, quoting the formula, I have a mark, then applying it. Remember, in this case now, you have the volume, you have the temperature. Pressure remains the same, so pressure is constant. With that, you have the initial, this is the second one, yep. I want to check, yes. Volume 2 will be given by temperature 2, here it is, temperature 2, because I'm cross multiplying here, temperature 2 times volume 1 is here, then divide by temperature 1, just that. After by doing that, my student get this answer there. It's a matter of substituting your values here for this, and then you get the value of volume 2 at this temperature, room temperature here. With that, follow the working I've done, my student there. Good. Determine the mass of ammonium chloride that reacted. This equation is what is guiding you. Ammonium chloride, you have calcium hydroxide, you have calcium chloride being formed, water and ammonia. The volume of ammonia is already calculated. So this is what guides you then the equation, the mole ratio. And there it is. We can start by working out the number of moles of ammonia. Volume divided by molar gas volume at RTP. With that, you get the number of moles. If we have the number of moles, we can use the mole ratio. It is 2:2. Otherwise, we can say it is 1:1. Remember, our interest is ammonium chloride. Moles of ammonium chloride, therefore, it is the same. The moles of ammonium chloride, it's the same as the number of moles of ammonia. Relative formula mass of ammonium chloride, it is, as I've done, 53.5. Mass, therefore, will be moles times RFM. And with that, you work out and get the answer there. That is how you're to do question 6C, Roman 2. And wow, finally we come to the very, very last question. Question number 7. Good. Give the names of the processes given in the following question. You have, this is methanoic acid acted upon by concentrated. If you see liquid, it is concentrated sulfuric acid, you get CO and water. Then you have hydrated sodium carbonate there, decahydrate. Exposed to air, you get anhydrous, or rather you get the number of water of crystallization molecules have decreased, like that. So which are these process? This is dehydration. Conversion of methanoic acid to CO and water, that is dehydration. Then the process by which salts or substances will lose water when exposed into the air is called efflorescence. Efflorescence, not efflorescence, efflorescence. Okay, moving on to question 7 part B. Sodium carbonate is manufactured through a series of reactions involving sodium chloride, ammonia, and carbon 4 oxide. Remember, my student, this is basically the Solvay process. But the question here is, ammonia is obtained by reacting hydrogen and nitrogen in the Haber process. State how the other two materials, okay, can be obtained. For example, sodium chloride and carbon 4 oxide. So how can we obtain them? If it is sodium chloride, we can do evaporation of seawater, or rather we can mine it from rock salt. Remember, rock salt is the main ore for the extraction of sodium, but it is basically sodium chloride, the highest composition of it. If it is carbon 4 oxide, we can obtain it by heating or burning limestone that is mixed with coke, or rather thermal decomposition of sodium hydrogen carbonate. Remember, CO2 is recycled within the same process. That is question 7b, well answered there, no big issue there. Concentrated sodium chloride solution that is saturated with ammonia is passed over carbonation tower or the carbonator. CO2 is bubbled through the reactions in the tower for the formation of ammonium hydrogen carbonate, which then react with the, okay, they are simply describing there what happens inside the carbonator or the Solvay tower. All that, we finally get sodium hydrogen carbonate and ammonium chloride. So, write the equation for the formation of sodium hydrogen carbonate. That is ammonium hydrogen carbonate and sodium hydrogen carbonate, the two. And there they are. Ammonia reacts with CO2 and water, the three, to form ammonium hydrogen carbonate. That is the intermediate reaction in the carbonator. Then the ammonium hydrogen carbonate react with the brine, sodium chloride, to get ammonium chloride and sodium hydrogen carbonate. There they are. You can see that, and it is simple that. But remember, the two reactions can be written as one. Ammonia gas reacting with carbon 4 oxide, water and brine, sodium chloride, to form the two. Sodium hydrogen carbonate, a soluble salt, but not as soluble as ammonium chloride. So when the carbonator is cooled, of course, it will come out in form of a solid. Describe how sodium hydrogen carbonate can be separated. Yes, remember this one is coming together with ammonium chloride. This one, it is how do we separate the two? These two. We've said one is a solid, the other one is a solution. So how do you separate? It's as simple as you're thinking. Sodium hydrogen carbonate is converted to sodium carbonate. There they are. The question was to describe, but a mention or a stating of the process was enough. Filtration, where sodium hydrogen carbonate is obtained as a residue and ammonium chloride is the filtrate. But our interest is to obtain the residue. If I want to obtain sodium carbonate from sodium hydrogen carbonate, thermal decomposition, you heating sodium hydrogen carbonate, you end up with sodium carbonate. That is that. One of the uses of sodium carbonate is to remove water hardness. Explain how sodium carbonate removes water hardness. State one other industrial uses of sodium carbonate. Yes. How do you do, or rather, how do you remove water hardness using sodium? You add sodium carbonate to hard water, then the calcium or magnesium ions that are responsible for the water hardness are precipitated out in form of their carbonates. Yes, either calcium carbonate will come out, magnesium carbonate will come out, and that one you will remove the two ions from water. Uses of sodium carbonate, as many as I've mentioned. manufacture of detergents, soaps, glass, paper, the sodium silicate, borax, sodium phosphate, among many. That marks the end of this very interactive revision here. I want to pass my gratitude to all my senior 233/2 examiners. I cannot say I'm Mr. Know It All. I'm not. There are other people who can do better than I've done. But thank you so much. All my counterparts in 233/2 and all fans of Dr. Sirme YouTube channel, continue coming back for more. Next I'll be doing the same year's paper 1, that is chemistry paper 1, the year 2023. Otherwise, God bless you. God bless you.